Good afternoon, everyone. We're about to get started.
Hey, you guys on the left.
Hey, you guys with the beer. Come on.
Sit down.
Got work to do.
We know that. Excuse us.
I want to thank you all for coming today. I'm trying to learn to talk here. All right, my time has started. Thank you all for sticking it out through the whole conference and coming to the final session of the day. We did ask them to bring the leftover beer over here, so something to look forward to. I'm John Ferguson. I'll be giving this talk. Mitch Goldberg was originally scheduled to give this talk, but instead he left AGU on Tuesday and headed off to Europe. And so I'm his stand-in. So what I hope to cover today is the launch of Suomi NPP 14 months ago, then go over a quick, well, not quick, overview of the program. And then the final part will be quick because I'm trying to go through some of the operational applications. So the data from the Suomi NPP and the Joint Polar Satellite System supports all four mission areas of NOAA. The obvious ones are climate and weather, but we also provide data which helps build strong coasts to withstand nature's fury and man's fury, and then data that helps fisheries and others build healthy habitats in the ocean. So the Suomi NPP is a bridge mission for both NOAA and NASA. For NOAA, it's a bridge from the POSE satellites, the Polar Orbiting Environmental Satellites, and up on the side you can see the heritage instrument from the POSE and the instruments that replace them in the S-NPP and JPSS era. And then for NASA, JPSS and NPP are a bridge mission from the Earth Observing System satellites, and you can see the heritage instruments there. The five main instruments on NPP and the first JPSS are listed here. We're going to have talks on the first four, so I'm not really going to go into them. Just we have the microwave sounder and infrared sounder, which work together to provide temperature, moisture, and pressure profiles. The VIIRS is our visible and infrared imager. Then the OMPS measures ozone. And then the fifth instrument, Ceres, provides data for the Earth radiation budget. And I believe Jim will talk a little bit about that. Just a little bit. Okay, all right. This next slide of instruments, no one will be talking about except me. So these instruments will not fit on our JPSS-1 bus, but NOAA is committed to flying them, and so we'll have what we call a free flyer. We'll have a separate satellite carrying these instruments. So the first two provide our search and rescue capability, and the third one, the Advanced Data Collection System, collects data from remote sensors such as an ocean-going buoy, or biologists might put a tracking device on an animal or something. And so when the satellite passes over, the data gets transmitted up to the satellite, and then the satellite sends it back down to Earth for the researchers to use. And then the final two instruments make up our total and spectral solar irradiance sensor. This slide shows the flyout for the polar environmental satellites. All of the satellites above, of course this isn't working now. Okay, all the satellites above the green fly in the afternoon orbit. And so I wanted to talk about the first one, GCOM, the Global Chains Observation Mission, Water 1. That's going to be flown by the Japanese, and it provides several water and ice-related products. We have a strong partnership with the Japanese, and because of that, we don't have to put a similar instrument on our spacecraft. Next down is just the Suomi NPP, and it looks like we covered up the legend, but the purple triangle is launched, the yellow is the CalVal time, and then the operational mission. So let's skip down to the green. Those are the METOP satellites. They'll be flown by EUMETSAT in the mid-morning orbit, and so they'll provide soundings and also imagery. And then at the bottom is the Department of Defense satellites. Their last launch was DMSP-18, and they recently announced that they will be flying DMSP 19 and 20 in that same, well, in an early morning orbit. And once the lifetime of DMSP 20 runs out, they'll have a new program, which they're currently trying to decide on. They're currently holding the satellite-based environmental monitoring analysis of alternatives to figure out whether they'll, build one spacecraft with several instruments or just have several small spacecraft with one instrument each. This is what we call our bubble chart. It shows the data products that we'll be producing from the JPSS program. The ones in black we inherited from the former NPOS, the National Polar Orbiting Operational Environmental Satellite System. And then in the red are additional ones which are included in the JPSS-1 Level 1 requirements document. And so there we list the products we'll get from GCOM, the Japanese satellite, and also additional ones we get from ATMS. In the NPOS era, we used to just say that ATMS worked with CrIS to provide the soundings, but ATMS can also provide several other products, and those are listed there. Most people will be getting their data from one of the operational centers, so either from NOAA, from the NOAA Satellite Operations Facility down in Suitland, Maryland, or the DoD is getting their data now from the Air Force Weather Agency. If you don't need timely data, you can also request data from CLASS, the Comprehensive Large Array Data Stewardship System. I hope I got that. But then the other way of getting data, if you have a satellite dish, is to download the X-band signal. The NPP and JPSS will be continuously broadcasting in the X-band, so if you have the equipment, you can pick up that signal. Obviously, just for the regional area, you're not going to be able to pick up global data, but for your particular region. And if you're interested in that, the link at the bottom there has the format of that data. And then our friends at the University of Wisconsin have come up with the Community Satellite Processing Package, and with that, you can process this data into data products. So this slide here is just, they stitched together several shots of imagery that are taken at different download sites. So it covers the entire continental United States, Alaska, and I believe they download in Hawaii as well, but that's on the edge of the picture. So our key challenges, we're not really interested in just building sensors and squeezing data out of them. We want to make sure that we're providing the right kind of data to our users, that it helps them build whatever end products that they need to fulfill their mission. And so one of the key ways that we're helping to do this is by establishing the JPSS Proving Ground. And the JPSS Proving Ground works with the GOES-R Proving Ground to make something bigger called the Satellite Proving Ground. And this next slide shows some of the key areas that we're looking at in the Proving Ground. So basically the way the program works is people that work with algorithms, researchers, and the users, they make proposals to us. They send them in. We send them out to the individual NOAA line offices, and they rank them. They try to decide, what's most important to them, and then depending on how much money we have, we try to fund as many of those as we possibly can. Obviously, the ones that scored highest. The next two slides just show how important polar satellite data is to the numerical weather prediction models. The way this is from the European model. And the way to look at it is they had like a baseline, and then if they added whichever row you're looking at, it reduced the error or improved the model that much. And so the interesting thing is what comes out on top is the microwave sounders and then the infrared sounders. And this again is from the Europeans, but on the left shows the 5-day model or 5-day model output. So the forecast from the 25th of October, which shows landfall for Sandy on the 30th. The middle slide, they reran the model, but without any polar satellite data, and that was their result. So they were forecasting for 5 days later that Sandy would still be well offshore. And then the third slide shows what actually happened. So it's a nice visual to see how important the satellite data is for the numerical weather prediction models. Okay, now I need to go in the hyperdrive. I've only got a few minutes. So these are some examples from the proving ground. So this is a couple of bands from VIIRS showing convective activity, which would help a forecaster, looking at thunderstorms in the afternoon and that type of thing. Next we have VIIRS imagery. We'll have a brief on this, but you can see the fires in the middle of that picture, and I believe there's a second shot. This is using the VIIRS day-night band. That's showing you the same fires in that red box. And other land type products that we provide are VIIRS surface type. And then for the oceans, we provide data on harmful algal blooms. So fisheries uses this, but when we have one of these blooms, you don't want to eat any of the shellfish. And then it's also not good for a lot of the fish in that area that eat the plankton or eat the algae. Also on the ocean, we provide ice data. So with this, you can make up ice edge data, which is very important to the ships operating in the northern and southern latitudes. And so this is just a summary of our key partnerships, which is what the whole polar system depends on. So for NASA builds our satellites. With the DoD, we provide data to them, and through their DMSP satellites, they provide data to NOAA. With EUMETSAT, they're providing the mid-morning orbit, and we also download their data at Antarctica. And then we provide data to them. And then we've already mentioned the Japanese at the bottom. And just in summary, the data from JPSS supports all 4 mission areas for NOAA. The data is important for both numerical weather prediction models and other forecast models. And then it's also important to the forecaster, the ones doing nowcasts for events happening right now or in the near future, then also for the climatologist. And then at the bottom, what's very important to us is user engagement. And with that, it didn't show up very well, but we'll be having a NOAA satellite conference in April in the Washington, D.C. area. So this isn't just for the people using polar data, it's also for the people using the geostationary data, and we also have some sessions on direct readout users. And so I think we have about 1 minute for any questions. No questions? All right, so we'll try to figure out the equipment here and switch over.
Start the timer. Thank you all for coming. I'm Jim Gleason. I'm the NPP project scientist. I think I know most of you in the audience. This is launch for those of us who are suffered the long slog. It was a for me, a 7-year project, and for folks I know in the audience here, it's well over a decade. So thank you all again for all of your hard work. I'm going to give a quick status of where things are, kind of go over through things, talk about a few things, advertise the talks that follow me in the session, and hopefully answer any questions. So we had launch in October, initial checkout in March, which basically means we had sort of a handover review where the flight project leads, the instruments basically work, and essentially the scientific checkout work begins. Currently, as of now, spacecraft instruments and ground system are all in nominal operations, which means everything works with the occasional hiccup, but by and large, things are working as expected. One of the things that's really important for everyone in the community to understand is our ground system is in the process of evolving and changing to support a true operational system. So what that means is they're in the process of redoing both the data distribution architecture as well as adding a whole bunch of features onto it to make it meet modern security requirements. The main effect that has us on our science users is that it really slows down the pace of change. So it's just something we have to get used to for the next year or two until we get the next ground system. In terms of data policy and release, all the instrument data is at the provisional level, which means it's basically worth looking at. The basic issues are identified, and it's all available from class. The EDR data, which is the data products, are going to start being available sort of from now through next spring. So there'll be lots of things to start looking at. This is where we were in March, which is basically just first light. Everything works. Everybody was happy. VIIRS data, CrIS data, ATMS series, and both of the OMPS instruments. So from March until now, we'll sort of talk about where things are. This is ATMS. ATMS is a pretty great instrument. It takes 3 of the AMSU instruments and puts them in a single box, which was sort of the advanced technology part of it. On the right side, you'll see this is basically looking at the cross-track bias, which the microwave retrieval folks are very sensitive to, and they're very pleased with the cross-track bias of ATMS. And the other thing they're very sensitive to is the noise, and the green bars are essentially the noise spec, and you want to be below the noise spec, and the blue is where we are, so you can see our blue values are all, black are all way below the green values. And Ed Kim, who will be talking at not the next talk, but the one after, will talk in a much more gory detail about ATMS and its data quality. The other half of the sounding package is CrIS. This is a very nice image from our friends at the University of Wisconsin, basically with essentially a first light spectra taken from a patch of clear ocean, and they shipped it off to Bill Smith and their friends and his colleagues down at Langley and Hampton, and basically they can do a retrieval. So we essentially had spectra and retrieval at first light, and then essentially all the good work starts. This is some, once again, analysis from the team members on the top from Utah State, showing essentially that we are well below our noise thresholds on CrIS. So it's a very low noise instrument, and everyone's really happy about that. And then as we start going forward is how do we connect the current instruments with the EOS instruments, which is sort of what the NASA science team is working on. And here's a piece of work done by Dave Tobin, basically looking at overlap data set in 3 bands, showing that essentially CrIS and AIRS are in agreement to about the 0.1 Kelvin level. This is these bars are basically at the plus or minus 0.2, so we're essentially at the 10th of a Kelvin, which for right out of the box is pretty excellent agreement for two instruments. Little piece of news. I'm not sure that whether Danae will talk about it. One of the things CrIS had done as part of the design was that they had truncated the interferograms on board, essentially sending down lower spectral resolution data. And you can see that here with the current operational data in blue and the high resolution data in red. And Larrabee, this is pictures from Larrabee-Stroh. And you can see, especially in the shortwave, all of this structure that comes up when you send down the high resolution data. This was something that had been a decision made long ago, and we worked pretty hard to basically get the program to essentially send down the native resolution of the instrument, which makes especially our friends in the shortwave extremely happy. So they're getting data from 2.5 wave numbers down to 0.625, essentially enabling all of the trace gas retrievals and things like that. So, and that data will start coming down spring of 2013 and be available from the the research users of the data set. VIIRS, everyone's favorite instrument, basically covers the waterfront from thermal data, visible data, and the day-night bands. This is a picture from our friends at Wisconsin, basically showing high-resolution sea surface temperature eddies off Greenland. Superstorm Sandy images with some pictures of the view of the sediment stirred up off the coast of Florida. And then the data set that's got sort of the new data set that has a lot of folks very excited, the day-night band, which is essentially taking the OLS data from DMSP and bringing it up into the 21st century. So a lot of people are very excited about that. That's just essentially a blow-up of the night lights in India. I'm going to walk through the thermal data first. It's from our friends at the NPP science team members at the University of Miami doing essentially sea surface temperature, and essentially they've got the sea surface temperature biases down to less than half a Kelvin, which is essentially current state of the art of where things are versus buoys. So in terms of thermal performance, the VIIRS data is looking very good. Ocean color, this is 3 views of the Chesapeake Bay from the operational algorithm, from the IDPS, a research algorithm from our NOAA colleagues, and the MODIS data. And you can see some that they all look about the same. There'll be an ocean color talk from Sherwin Ladner at NRL later in the session to go in more detail. There was a lot of discussion about this early on. Would it work? Would VIIRS actually give you ocean color? And you can see pretty much out of the box it looks fairly reasonable and basically gives people a sense that there's data here that they can work with. And once again, that's sort of where we are, is essentially that was in the coastal oceans and Chesapeake Bay, complicated waters, from the NASA Ocean Color team, which sort of is looking at it globally. This is VIIRS and MODIS 8-day composites, and looking at essentially the blue water ocean chlorophyll. So once again, if you're trying to do multi-satellite data sets, is VIIRS good enough to carry on the MODIS ocean color data set? Here's 2 images. Here's the time series with MODIS and VIIRS, and the difference on the right. So we're down in sort of in the 10% range already. So this is plus 80-20. So within the first year of data, things are looking good, and there's data sets folks can work with. OMPS-LM, just a brief advertisement for PK's talk. This is a new measurement for us. Basically, by looking at the limb of the Earth, you can infer an ozone profile. This was shown earlier that, in fact, we're getting pretty good agreement with MLS, and PK will talk more about that. Sort of the bread and butter mission is the other side of that instrument, which is the Nadir Mapper. This is this year's ozone hole, and essentially we were, mapping this year's ozone hole, and did the standard release that it was not a particularly large ozone hole this year. And then once again, what the team does is try to do the intercomparisons between the operational algorithms, research instruments, doing the quantitative studies, and trying to understand the differences both between the instruments and the algorithms. In addition to the operational products of ozone, the NASA team is continuing research products like SO2. I think OMPS, with its unique spectral characteristics with no spectral break at 310, will be a very powerful SO2 instrument. And this is some data from Kai and the folks showing essentially a unpronounceable volcano in Africa, showing pretty good agreement with OMI data. And these data are available from the NASA SO2 team. Our friends at Langley, very excited. They got Series FM5 on NPP, added late to carry on the series data record. This is their first light images. I was successful in holding their feet to the fire and actually getting an image out of them of actual net radiation data. And essentially, they've released their first set of data now, and it's available through the Atmospheric Science Data Center down at Langley. The first big data set, which is sort of their fused cloud aerosol VIIRS data, will be coming sort of at the middle of next year, rather. So you can download series data and start playing with it, and the fully loaded product will be ready in the middle of next year. And I think that's all I have on the quick update for NPP. If anybody has any questions, I'd be happy to take them. Thank you.
I think we have a couple minutes for questions. Go ahead.
So CrIS will be able to see you now?
Yes. We will take the data, and then we will sort of work out how to do it, but we already have a number of folks. Larry Bistro's actually already done a CO retrieval on the 5 orbits of data that we have downlinked. So I think everyone's really excited about that. Any other questions? Okay. With that, we'll move to the next speaker.
Okay. Next up, we have Denise Tremblay. And let's hope this all works.
Is there a point? That's a pointer.
Yeah. It's a very, very bad
Very,
angle.
very bad angle. Okay, I will.
So
I want
Yeah, it might be easier to move the
to move the mouse.
Yeah.
Okay, thank you.
Oh, no, looking at the screen is easier.
Here. Yeah.
So we need to this.
Yeah.
Well, good afternoon. My name is Denis Tremblay. I'm affiliated with NOAA-STAR down in Washington, D.C. And I'm going to talk more about CrIS instrument and the calibration and validation activities related to the CrIS instrument, what we do at NOAA-STAR. Just give you an introduction about what the CrIS instrument is. It is a Fourier transform spectrometer, and what I would like to point out, there are 3 bands, the long wavelength, mid wavelength, and short wavelength. And as Jim just mentioned earlier, the spectral resolution of 0.625, 1.25, and 2.5 respectively. And later on in 2013, we will be downloading the raw resolution, high resolution at 0.625 in all 3 bands later on next year. It is, as I said, it's a Fourier transform spectrometer, and it's a very lightweight. It has some very neat characteristics compared with the other airborne instruments that are flying like this. For example, we have a neon lamp that gives us a reference for the laser wavelength. We have an OPD locking mechanisms, meaning that when we sample the interferogram, it starts sampling exactly the same optical path difference, and this way we don't need to perform sampling phase alignment on the algorithm. We also have a dynamic alignment of the push-wing mirror, meaning that the optical axe is oriented right in the center of the field of view 5, and that's increased the signal-to-noise ratio to as much as possible. The data acquisition here, we have what we have is a 3x3 field of view, and each time we have a sweep of the mirror here. We're acquiring one field of regard followed by another field of regard And in a period of 8 seconds, we acquired a total of 30 field of regard, and the SWAT is 2,200 kilometers here. On the global day, on a day we have over 95% of the global coverage. As part of the validation activities, we do what is called OMPS minus calc. Here we have OMPS, which is the CrIS instrument. We use calc, which is a CRTM. For those who are not familiar, CRTM is a community radioactive transfer model. It's the one that is used by NWP for the weather forecasting at NOAA. So in other words, when you turn on the TV in the evening, you see the weather channel. What you see is CRTM under the hood. So what we do is we take OMPS minus calc for the individual field of view, and on the other term is OMPS minus calc for the average for all field of view, and that gives us a relative radiometric assessment for each field of view. As a result, we see there's a very, very good agreement for each field of view here for all bands and all field of views. There are some discrepancy in the short wavelength, and we are looking at this time. Another way to do validation is to look at what is called simultaneous nadir overpass. We compare the CrIS and YASI at this time, and the simultaneous nadir overpass is when both instruments are looking at the same location at the same time. And as a result, we found that CrIS minus YASI, we have a very good agreement overall of 0.2 Kelvin or better. We have a discrepancy in the short wavelength at about 2400 wave number here, and we are looking at this time. So, we also did CrIS minus CRTM, OMPS minus calc directly, and we found that over the window channel between 800 and 980 wave number, we have a very excellent agreement about 0.2 Kelvin. In the mid wavelength, overall the average is pretty good, but we have some shortage about the minus 0.8 Kelvin here in about 1300 wave number. In the short wavelength, we see a lot of spectral feature, and we're looking at this time as to what the root cause are. We also did what is called the double difference. We do OMPS minus calc for CrIS, and the second term of the equation is OMPS minus calc, but we use IIZ at this time. IIZ has been converted to the CrIS radian, so we can compare apples with apples. The result is that we have overall a very excellent agreement in the long and mid wavelength, and we see some discrepancy in the short wavelength again. That we have a discrepancy for day and night around the 2400 wave number. The difference around the 2500 wave number here is probably caused by the BRDF function, where we will have day and night discrepancy on the model. The CRTM just take an average of sea surface temperature here. We also have a NOAA-STAR, a web-based trending and monitoring system. We monitor over 55 parameters. I'm just going to show some of them. Here we have the neon lamp laser wavelength that is monitored, and so far since the beginning of the mission, we have seen a trend of about 1.5 ppm downward that just started in September, and it is not a cause for alarm at this time. Back in June, we also looked at the data quality flag, and we changed our parameters, a threshold parameter tuning for data quality flag. And before July, we had over 60% of the data quality flag where flag has degraded. And after we performed the tuning on the threshold values, that percentage went down to about 1 to 2%. Other parameters that we monitor are the ICT, which is a black body, the temperature of the black body. We also monitor the radiance. For example, a 900 wave number here. This is a global map. The third plot here is the the CrIS overall data quality flag, and the blue indicate that these are valid. As Jim mentioned, we have now the noise. The noise is excellent everywhere except for one field of view, which is the mid-wavelength field of view 7, which is above the specification. But I must say that if you are a user for the CrIS data, I wouldn't be afraid to use that detector, even though it's more noisy. Otherwise, it's just excellent noise. We went a bit further. We wanted to know what is the full covariance matrix for the noise. And the method here, we use the Earth scene and the PCA analysis, and we're able to extract that full covariance matrix. I'm not showing the result here for mid-wavelength, which shows that the covariance matrix is diagonal dominant, and the off-diagonal terms have a correlation factor of about 0.06, which is very, very good. On the plot on the right, I'm showing that, excuse me. On the plot on the right, I'm showing that the diagonal of the noise as derived from the Earth scene compared with the noise derived from the ICT and the space, and they match very, very well together. Another method that we use is to look at the geolocation. We're using VIIRS in order to assess the accuracy of the geolocation for CrIS. And the method consists to convolve the CrIS radians with the VIIRS RSR function that we see here. The second step is to take the VIIRS pixel and to convolve it with the CrIS footprint. So we just average the VIIRS radians within the CrIS footprint. So now we can compare CrIS versus VIIRS. We form a cost function, and by shifting the VIIRS image with respect to CrIS, and as a result, we found that there was an offset. CrIS had an offset of 4.5 kilometers, so we were not happy because we don't meet requirement at that time. So we'll dig further, and we found that, well, there was a software bug. So we fixed that software bug, and as a test case, we can see the Persian Gulf here. We see on the left plot is the Persian Gulf, the CrIS radians. On the middle plot, this is the CrIS minus VIIRS before we applied the correction for the software bug, and you can see the coastline of the Persian Gulf here. And when we apply the correction, now that coastline just completely disappeared. And we believe at this time that we achieve an accuracy about 1 kilometer for the CrIS instrument. Another work that we did was to assess the spectral accuracy of the CrIS using CRTM, and the method consists to shift the spectrum with minute increment until we achieve the highest cost correlation factor with respect to CRTM. The result is that CRTM has a 3 ppm offset on the spectral calibration in the long wavelength, and also a 4 ppm offset in the mid wavelength. So these values are very, very good. They're excellent, and we meet a requirement, which is 10 ppm. As a summary, NOAA-STAR calibration activities are contributed to the CrIS post-launch assessment on all aspects of the radiometric accuracy, the spectral calibration, the geolocation, and the noise. As Jim mentioned, we're now provisional status, meaning that the user, we feel confident the user can start using the data on CrIS, which I strongly encourage you to download it from class. And we expect that the validated maturity level would be achieved around June 2013. So that, are there any questions? Thank you.
No questions?
No question.
Okay.
Okay, thank you.
Thank you very much, Danny. All right, so now we'll move from our infrared sounder to our microwave sounder. And so we have Ed Kim from NASA. Let me pull.
full screen.
Okay. So this will be.
Okay. Well, good afternoon, everyone. My name is Ed Kim. I'm at the Goddard Space Flight Center, and I'll try to give you some information about the current status of ATMS. I did want to acknowledge the folks that you see listed there. These are the folks comprising the SDR team, and really what I'm showing you is really, their work. It really is a very good team effort. Okay, this is a quick outline. I think Jim already showed you, actually both John and Jim showed the importance of microwave sounding. You saw the impact or the error reduction due to the inclusion of the microwave sounding information, so I won't repeat that. I will go into a little bit of instrument characteristics. I know it's late Friday afternoon after a long week, so I put in plenty of pictures, color pictures. And then I'll try to show you, I'll try to sneak in some actual, technical stuff in there while you're not paying attention. And then wrap up with a summary. So as I promised, I'll skip that impact stuff. The one thing that, the other application aside from weather is climate. And this is a little bit particular to the microwave sounders just because we've had microwave sounders since the 1970s in orbit. And so at the bottom of this slide you see well, actually both the top and the bottom, you see some attempts to stitch together sound or satellite observations over the entire period starting from the 1970s. And of course, the spatial resolution was a lot worse back then. The sensitivity was worse back then. Everything was, has gotten better with time. The orbits were different, so there's a lot of adjustments that need to be made. But this is typical of what I guess anybody or any instrument faces if you're trying to construct a climate data record. So in any case, this has been done with the sounders, and you can see at the top there, at least according to a couple of the teams that have looked at it. For the RSS team is Frank Wentz at Remote Sensing Systems, and the UAH team is the team down at University of Alabama, Huntsville. So you can see the red and the blue trend lines there indicating potential statistically significant climate trends over this period. So this is the other application of the data. And for this, of course, you need extreme accuracy that the instrument itself cannot provide straight out of the box. So the only way you get this is through a lot of scrubbing and a lot of correlating, different kinds of data together and just sanity checks. Excuse me. So here are some pretty pictures to start you off with. These are from Hurricane Ernesto. You can see the VIIRS, the color image in the lower right. So if all you have is a visible sensor, all you're going to see is the tops of the clouds. And if you have clouds, you're not going to see the surface. Whereas the microwave sensors, at least at these microwave wavelengths, do penetrate into the clouds to different depths. And so you are able to get information about what's going on inside the hurricane, and that's especially valuable if you're trying to figure out, the intensity, what's going to happen with it, and which way it's going to move, what's going on at the ocean surface or the land surface, etc. And here are some more images, again, trying to show you, taking advantage of the fact that the atmosphere absorbs depending on what exact wavelength you're at. Okay, so as promised, some pretty pictures. As Jim mentioned, ATMS combines 3 previous microwave sounders, all of which were similar-sized boxes, if you will, and they've now all been combined into a single instrument, which was quite an engineering feat in and of itself. However, I will note that ATMS was first proposed in the 1990s. And was selected back then. And then of course, like any other spaceborne instrument, at some point you freeze the design so that you can build it with low enough risk. So the technology that's embodied in ATMS is representative in a lot of ways of 1990s technology. So here's, again, pictures of the predecessor set of instruments on the left, the AMSU A's and the MHS sitting on their satellite bus, and then on the right side you've got ATMS with its protective red shield there sitting on the NPP bus. And you saw this picture before. I won't go into those details except to show you this. So this is, on the left-hand side of this chart is a list of the channels, specific microwave frequencies, polarizations, and so forth, for the predecessor instruments, and then the corresponding ones in color on the right-hand side of the table for ATMS. So by and large, you can see where you see green, they're exactly the same, and as the colors progress towards red, there's slight differences. Maybe the frequency is a little bit different, or the polarization is different. And then only in the two red cases is there something completely new in terms of channels. And then the other, excuse me, I guess important aspect of ATMS is the beam width. You squeeze a bunch of channels, microwave channels, into a small package, and the laws of spatial resolution or antenna beam width get you. So the first two channels have a 5.2 degree 3 dB beam width, and they get progressively better as you go higher in frequency, as you would imagine. But on the right-hand side are, I guess, the improvements, or the improvements over the predecessor instrument. Better spatial sampling. So even though the beam widths may be what they are, as you see on the left, you can sample as often as you can program your instrument to sample. So we do sample high enough at a high enough rate to get Nyquist sampling, even at the high channels. And also the wider swath, which eliminates some gaps in a global image. This is just a cartoon showing that ATMS is a cross-track scanner, so I'm not going to dwell on that. And these are sort of overall specs for the instrument, what it weighs and how much power it consumes and so forth. It is a low data rate instrument. All the passive microwave instruments tend to be quite low data rate. So the NASA provided ATMS, and I guess that was the one instrument on NPP that NASA decided to provide. It was actually designed and built by Northrop Grumman Electronic Systems, the old Aerojet, and ATMS was the first one that showed up for the party. It was delivered back in many years before launch. And we waited for our friends, the other instruments, to join the party. And we've been in orbit now for about a year, or just over a year. The second ATMS unit is under construction. We'll be doing thermovac tests of the whole instrument this coming spring, and launch is, I guess, scheduled in 2016, if I'm not mistaken. And so, some of the key challenges relative to the predecessor instrument, in addition to just shrinking 3 packages into one, had to do with putting, at the time, the latest microwave integrated circuit technology in there to improve reliability and noise performance, and then also just the rotating mechanical scan mechanism. And I had already mentioned the other two down there. So here's some images. On the left-hand side, you see ATMS. On the right-hand side, you see the predecessor. You notice the gaps there near the equator for the predecessor AMSU, and then, as I said, because of the slightly wider swath on ATMS, those gaps go away. But other than that, you see pretty much the same thing, and that's what you would hope for and what you would expect for the same channels. And then we have a number of data records. They all have names that end with DR. Right now, the sensor data record is the same as the temperature data record for ATMS until we get final numbers for antenna beam efficiency and scan bias corrections. And as you heard from the previous speaker, most or all of the instruments have achieved provisional status with various caveats. Our NOAA colleagues have been doing comparisons against model-based output, and here's one of them. Most of the NWP models are particularly sensitive to bias, so in this particular comparison exercise, they were really focused on looking at bias statistics. And so you can see from the histograms that, you know, they want to end up in the sort of green bordering on yellow regime, and pretty much you can tell from the global images that they do, so that's good. You already saw an example of this online monitoring system from our colleagues at STAR, and this is invaluable. It's automated, and you can look at you know, internal engineering numbers, extra, you know, science output numbers, and it really helps us make sure things are working correctly. This was a complicated chart, and I'm not going to go into a whole lot of detail, but right after launch, one of the settings that we had to choose was there was a choice of 4 different scan profiles, and those are indicated with SP1, 2, 3, 4 in blue on this chart. And they really just chose the exact position of the cold space view that we use for calibration. Now, cold space view, as the name implies, you want to see cold space and nothing else. Once in a while, just due to orbital mechanics, the moon drifts in your field of view. And so the horizontal rows of black dots are to scale the size of the moon relative to the big circles, and the circles are to scale the size of the antenna beams looking out into space. So this was an exercise of looking at the impact of lunar intrusion, but also, and probably even more important, SP1 is a choice of look direction that's closer to the spacecraft itself, and there was a potential for seeing parts of the spacecraft or seeing things reflected off parts of the spacecraft, which would then potentially impact your calibration. Whereas SP4 would be further away, but then closer to the Earth's limb. So there was during commissioning, there was an exercise to look at that, and we ended up going with SP1. Jim, I think, has already noted that the noise performance is very good. It's meeting spec. Temperature performance is also doing well. We were able to convince the project to do some maneuvers, and we've used those for calibration, including this pitch over maneuver. You can see the big blank, dark blue area is blank when we were flipped upside down. And geolocation is working out really well. Our colleagues at Northrop Grumman AS have been looking at some remapping that figures in the overall data processing. And our colleagues at Raytheon have been helping us a lot with testing of changes to the operational code. So I see I'm out of time, but the ATMS has been working well. We were the first instrument turned on once we got on orbit. We produced the first light image for the entire JPSS program. And things have been working essentially as expected and according to spec for this first year, and we look forward to more data, a second instrument when JPSS-1 launches, and continuing to provide valuable information to our operational forecast users and the climate folks that want to try to construct those long data records. Thank you.
We've been running efficiently, so we still have time for a question if anyone has a question. Nope. Okay. All right. Thank you very much, Ed.
Thanks, Ed. Next speaker is PK.
Well, I'm going to be talking about an instrument on Suomi NPP that doesn't really have a pose or EOS heritage, except that the SAES 3 did make some measurements like this. Also, it is only instrument on Suomi NPP that looks at the limb rather than the nadir direction. I'm actually a newcomer to this project. Glenn Jaros has been in charge for a long time of the SDR product, the Level 1B product from this instrument, and Didier Raoul, who retired from NASA earlier this year, has developed the retrieval algorithms. So I'm just going to be representing the work that these two people have done. So as I said, that this instrument is actually part of the OMPS package, the ozone monitoring and profiling suite. It is one of the three instruments there. The native mapper is very similar to the TOMS, although it has a much better capability for doing SO2, volcanic SO2. The native profiler is very similar to the SBUV instrument, although it does have better capabilities and it may be able to do better ozone profiling near the topopause. But the limb profiler is a new type of instrument, although there have been previous measurements, particularly as I mentioned, SAES-3, but also OSIRIS and Skimaki has produced long-term data set. These are European and Canadian instruments. And GOMOS, which is a stellar occultation instrument, also had produced some limb scattering data. Now, the main advantage of this instrument is that it has a pretty high vertical resolution, about 2 kilometers, which is even better than MLS. So in principle, it can actually do much better job. The other thing is that it has 3 different slits. So basically, if you look at it, can I use the pointer here? So it actually makes a okay.
Or you can use some.
Oh, I can use this one. Okay.
Yeah.
So it's actually taking too much time. Okay, here. So it actually produces 3 different images about 250 kilometers apart. So in principle, it has a much higher spatial resolution than MLS can provide you. So there are possibilities of doing studies that have not been possible to do from, for example, MLS. Has a pretty nice ground sampling. Okay, this one here. Okay, here. Okay, now finally. Vertical sampling is 1 kilometer, the vertical resolution is 2 kilometers, and there are 3 of these slits that allow you to make measurements that are 250 kilometers apart. The team has a particular charter, and this is our charter right now, is that one of them is to produce a validated ozone profile. That is the only real EDR product we are producing from this instrument. And our goal is to do a long-term monitoring of ozone. Although, as I said, there are other things that can be done as well. But right now, this is our primary objective. And our goal is to achieve data quality very similar to the Aura MLS, not necessarily better than that. We're also going to release the validated radiances. And there are certain research products that can be produced from it, although we don't really have funding to do them. But if there are people who can bring their own funding, they can actually take the radiance data and produce them. We know we can do a pretty good job with tropospheric ozone by combining the limb measurement with the nadir measurement. We already know the stratospheric aerosol is a very high quality product. We're actually producing it sort of as a part of the ozone retrieval, but it is not a product that we have released yet. You can also do polar stratospheric cloud, polar mesospheric cloud, and in principle, with a little bit more work, it should be possible to do 2 kilometer vertical resolution temperature profile and even do gravity wave studies. But again, these are more challenging activities, and we have not been funded really to do any of that yet. The main problem with this instrument is that compared to some of the previous instruments like Hurdles and MLS is that for this instrument, the limb is actually mapped on the CCD detector. Most of the other limb instruments in the past have actually been scanning the instrument at the limb by looking at very narrow field of view, and they vertically scan it. But in this case, the instrument actually makes a mapping of maps the limb on the CCD. And there was a lot of concern prior to launch that this would produce a stray light problem. And there are stray light problems, but I think we have a pretty good handle on that. The other problem is that the image on the CCD, because we are covering a very long wavelength range or a large wavelength range from 280 nanometer to 1 micron, there is an optical distortion, chromatic aberration that makes the limb image shift with wavelength. And finally, the problem is that you have 6 separate images that you are producing, from the 3 slits, but there are also 2 narrow and broad slits to cover the dynamic range. And we have found that these images, they shift in the CCD along the orbit as well as over time due to the change in the telescope temperature. That was unexpected, but this is something that we have to account for. This shows you the stray light. The red colors are basically represent where the stray light is more than 10%, and the other colors represent stray light less than 10%, and these are the areas where we can do a pretty good job. So the stray light is not as bad as a lot of people feared, and Ball Aerospace, who built this instrument, did a very, very careful job in characterizing on ground the stray light problem. So I think we have a pretty good handle on the stray light, although in the red areas we may not be able to do very much of retrieval. So the lowest wavelength we can go to is about 290 nanometer, and there's problems at 1 micron because you have very, 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 very low signals. The other problem, as I mentioned, was the shift in the images. You can see here that this instrument has actually 6 different slits or 6 different aperture, 3 along the azimuth direction or the yaw direction, and there are broad aperture and a small aperture to cover the dynamic range. And these things shift as you go along the orbit. As you can see that as the temperature of the detector changes, the temperature of the baffle changes, these images shift by up to about half a pixel or more. Fortunately, the central slit does a very good job. Central slit doesn't have very much of a shift. So for the first release, we are focusing only on the center slit. We are going to come back and do the other 2 slits later in a later release, but for the time being, we are focusing only on the center slit for this particular reason. There's also a time-dependent shift. You can see here as a function of orbit number, there has been a shift with that as well, although these are much, much smaller in magnitude than the other changes are there. So again, these can be handled. We have enough information in the measurements to be able to correct it. So in the release that we have just, the product that we have just released on November 1st, we have several corrections in there. We are making a detector correction of various kinds, such as dark current and other correction. We are applying a stray light correction based on the pre-launch measurements done by Ball Aerospace. But as far as the wavelength correction is concerned, we are not applying this thermal shift right now. We are only applying a static correction to account for any changes between the pre-launch to post-launch. There was a significant shift in the wavelength there, but we're not accounting for the temperature dependence because, as I mentioned before, for the central slit, this is not a big issue. And we are focusing right now on the central slit. Same thing with the tangent height or the correction for the vertical image, and that also is only a static correction. We are not applying any kind of a thermal effect correction here. And the radiance data interpolated to uniform wavelength and altitude grades to account for this optical distortion I mentioned. Okay, in the case of EDR, the main problem that we have with the EDR is that this instrument is designed to measure ozone density versus altitude, whereas, for example, MLS and hurdles and other instruments that have provided good data before, they have been doing mixing ratio versus pressure. But this instrument has been designed to do ozone density versus altitude, very similar to what SAES has done in the past. But the problem we have is that we can derive the density pretty accurately from our measurements, but the altitude information comes from a star tracker that is on board the spacecraft. But that star tracker is not at the location of OMPS, but it's location of VIIRS. So the concern was, or has been, and still is, that because of the flexure of the spacecraft structure, we may actually be getting a significant error in our Z estimate, the altitude estimate. So because of this, we had, prior to launch, developed some techniques to use the limb measurement itself and combine that with the geopotential height measurement from NCEP to be able to estimate what kind of error that is. That result shows that the error is not very large, but the problem is that we have a sensitivity of only about 500 meters. We can't really do right now much better than 500 meters. So at least to the 500 meter level, this doesn't appear to be a big problem. But it could be a problem at a lower level than that. And 500 meter is just barely good enough to do this work. The other problem is that if you want to convert this density into mixing ratio, then you need to know the geopotential height and the temperature everywhere, not just at some location at 10 hectopascal. And we are totally dependent now on the temperature data that comes from NCEP. And that produces extra error in producing this quantity. So this makes it difficult for us to compare our profiles with MLS, because MLS produces ozone mixing ratio versus pressure. So we have to look into these problems as time goes on. So for the first release, we are not making any tangent height correction due to possible spacecraft flexure. As I said, that the error is probably less than 500 meters, and we still have to figure out whether there are errors of a smaller magnitude than that or not. We are doing an ozone and aerosol profile retrieval simultaneously, and the aerosol comes out as a very nice product, as a byproduct, although we are not really have been funded to produce an aerosol product in itself, but it is a byproduct and it looks pretty good. As I mentioned before, that in order to convert to mixing ratio, we have to use the geopotential height and temperature profiles from NCEP, and that we are doing that right now, but we do not know how much error it introduces in this technique. So I set a data quality goal for this instrument. We said that we are going to release the first version of this data set only if I can meet this objective. So I set this objective and basically said that our team has to show that we can at least derive the daily zona mean ozone mixing ratio at about 10% level compared to Aura MLS or 100 ppb, whichever is larger. If we cannot meet this goal, we are not going to release the data. But it turns out that we have met this goal, which, by the way, is about the state of the art in this field. 10% 100 ppb is about the state of the art for ozone measurement. So this is pretty tough to meet. What I'm saying here is that we have largely met this goal. Not everywhere, not all altitudes, but largely met the goal. So that is why we have decided to release the data. So this is just one example. I can really show you lots and lots of examples. We are actually going to produce a validation paper. This is showing you, again, the ozone mixing ratio versus pressure. The red line is from MLS. It's a monthly zona mean for June 2012. And the blue line is from OMPS. Now, you see that the OMPS has a little bit more structure than you get from MLS. That is most likely not because the OMPS has more vertical resolution, but I suspect that it is because of the temperature accuracy from NCEP that we are getting. NCEP temperature doesn't have the high vertical resolution that we need in order to produce it. So I suspect that the structure is partly at least due to NCEP temperature profile errors, although we need to really look at that. There may be other possible sources of error. But you can see that within the lines that I have drawn here, 10% plus or minus 10%, we are actually meeting this objective pretty well. And this is just a typical example. If you look at other latitudes, other months, other seasons and everything, the results look pretty much about the same. So I really don't have a whole lot to say other than to say that most of the places we are actually doing within plus or minus 10% of ozone, which is actually quite remarkable because this instrument has very little heritage going back in the past. So to be able to do this after 9 months, I think it really is a credit to the work Didier has done in developing the algorithm pre-launch. So it is essentially the pre-launch algorithm with almost no tweaking that is producing such high quality ozone profile data. So this is my summary, very brief summary of where we are in terms of the data quality for release 1. The instrument performance is pretty nominal. There have been no surprises except for the thermal shift that I mentioned, which is a surprise. The pre-launch analysis did not indicate that there will be this thermal shift. But the thermal shifts are overall pretty small and they are correctable. So although we are not correcting it in this release, we do plan to do that in the next release. It is not a problem. The ozone data quality largely meets the release goal that I set, which was 10% 100 ppb. But the main issue right now is we need to evaluate how good is the geopotential height and temperature profile that we're getting from NCEP. And that may be the biggest source of error we have. Ultimately, no matter how good a job we do, this will be ultimately our limitation, particularly in the upper stratosphere and mesosphere. Okay, so this is where we are right now. We have released the EDR and the SDR, the level 1B and the level 2 products on November 1st, 2012. The data starts from April 1, 2012, because before April, the data were pretty spotty. The SDR contains only gridded radiances. We don't provide raw radiances. EDR contains ozone data from the center slit only. We are not really focusing on the other two slits yet. And we're not providing aerosol data, although aerosol data are coming out as a byproduct of this retrieval algorithm. We plan to release a data quality assessment document in around January 2013, and a paper comparing the results from this instrument with MLS and Odin Osiris is in the draft form right now. So this is basically my last slide, showing you this is where you get the data from, and I thank you for your attention.
Any questions for PK?
Okay. Okay. I'm Sherwin Ladner with the Naval Research Laboratory. I'll be talking to you today about the evaluation of some recent VIIRS sensor performance in the coastal ocean. I'd like to thank my co-authors and acknowledge our sponsors at the JPAS program office. What did I do? Okay, it's just a blank. Yes. Okay. Our objectives are to evaluate current our NRL processing for the Navy and also the IDPS environmental data outputs products. Talking about the normalized water leaving radiances, chlorophyll, and backscattering. We're also going to use Coastal AeroNet Ocean Color time series for normalized water leaving radiances at the AOT Venice, Italy site, and calibration and validation ship cruise data that was collected in Hawaii, Gulf of Mexico, U.S. East Coast, and a Slocum glider deployment off of the coast of Panama City, Florida, and some intersensor comparisons with MODIS for the radiances and the biooptical properties. So there's two software packages that we're going to be evaluating for ocean color processing. One is our Navy software, which we call M2Gen. It's developed using NASA's L2Gen, and it's our research and development software. The SDRs that we're using are from AFWA. The atmospheric correction is the Gordon-Wang NEAR-R using the 80 aerosol models, and we're doing glint and cloud removal, and then water algorithms are from the QAA algorithm developed by Zhongping Li, the coastal iteration. The other software package is the NOAA operational IDPS package from which are the products that we're getting from class and the versions of those. So our research, we're using our research software with the Navy to evaluate the VIIRS sensor and identify issues and improve the IDPS EDR outputs and software. So the image on the left is the current IDPS. It's a chlorophyll image for the U.S. East Coast on August the 3rd. You can see that the pixels, there's a lot of masked pixels. And the future version is on the right, which will be coming online in January of 2013. And that version will be 6.6. And as you can see, you know, they're getting a lot better results. And if you compare that to the Navy processing from N2Gen, they agree pretty well. But in the coastal areas, we're getting higher chlorophylls from the IDPS outputs. And so the value, for example, at the Martha's Vineyard Coastal Observatory for chlorophyll is 13 milligrams per meter cubed. With the NRL, we're getting a value of 4 milligrams per meter cubed. The cloud masking, they're both similar. And if you look at it for the MODIS Aqua, the value of chlorophyll at the MVCO region of MVCO location of 4.7. This is a time series of chlorophyll from the Martha's Vineyard mooring. As you can see, the image that we were just showing was from August of 2012. And if you look at around August of 2011, the chlorophyll range is about 4 to 6 milligrams per meter cubed. So at the MVCO location, if you look at the normalized water leaving radiances, the spectrum, you know, the IDPS values in the blue are just are lower than the N2Gen outputs. and some chlorophylls in the coastal areas are really are higher, a lot higher. So the IDPS, chlorophyll values are seems to be a little high, and N2Gen retrieved our Navy processing. The chlorophylls are closer to the MVCO data. But VIIRS sensor is showing good agreement with the observations. This is a scatter plot of VIIRS versus MODIS for 4 normalized water leaving radiance channels: 412, 443, 486, and 551, and also backscattering at 551, and chlorophyll at the chlorophyll OC3 product. And this is a scatter plot of VIIRS versus MODIS Aqua. This is our the Navy N2Gen processing, both sensors. And you see they agree very well and within time and space uncertainty of the products. We have available a global AirNet ocean color network. We have 15 sites right now that we're using. They're CPRISM radiometers mounted on platforms. There's protocols for the installation, collection, and processing of this data. And I'll be showing you a time series from the AEOT site of normalized water leaving radiances and the matchup with the CPRISM there. So the top plot is normalized water leaving radiance at 412. So we're plotting Julian day versus normalized water leaving radiance. The blue are the CPRISMs, the red is the VIIRS, and the green is MODIS. So there was a lookup table change in July the 19th for MODIS. So you see there was a version 5, this is the MCST lookup tables. So version 5 MODIS, they were having issues with MODIS in the blue channels you see here for 412 and 443. But after the lookup table change, MODIS starts to fall in line with the VIIRS and the CPRISM. But overall, I mean, the CPRISM versus the VIIRS, the matchups are really, really good. So CPRISM versus MODIS, the slopes are are high with the high R squared. It's the same with CPRISM and VIIRS and MODIS and VIIRS. They all are similar. So version 5, I mentioned the MCST lookup tables. Version 5 was done with a CWIFS cross calibration, and version 6, the correction was done using desert sites, and that was done by NASA. To our CalVal cruises, we're looking at the VIIRS, N2Gen processing, MODIS if available, and also the IDPS if available. So on the top, on the left-hand side are the images from September the 11th off the coast of Honolulu, Hawaii. The 2 stations that we're looking at, as you see here, and the bottom image is from the IDPS. So the pixels there are masked. We're not able to get retrievals for the IDPS images. But if you look at the 2 stations from the 11th, they do agree very well. And MODIS, the second station for MODIS was cloud contaminated, and also the IDPS was masked. If you look at on the 12th, which are the images on the right, this is chlorophyll, is the background image. We had 1 station, and as you can see, the matchup is pretty good as far as the normalized water leaving radiant. This is remote sensing reflectance, I'm sorry. So the same thing on the 15th, we had 4 stations, and on the 17th, we had 2 more stations. So the images on the top are from the 15th, and the same thing, we're having issues with the masking of the IDPS output, or EDRs, and also the blue lines are the VIIRS And the green line's the VIIRS, blue line is the in situ data. So as you can see, these were done with a HyperPro instrument. I agree very well. This is a cruise that was conducted in the Gulf of Mexico and off the coast of Florida, and also along the U.S. East Coast. So we're going to show stations from both regions. We had one station on July the 26th, which is located here. Also, the red is the MODIS, the green VIIRS, and the blue is the in situ. So the matchup is also pretty, they're agreeing very well, and the same from the 27th. Off the coast of the East Coast, they had two stations near the Gulf Stream. The MODIS images were cloudy and glint contaminated for these 2 days, the 5th and the 9th. And also, you know, they're agreeing very well. We had one IDPS retrieval on August the 9th, and, you know, there's a little bit of, the IDPS output's a little bit lower in the blue channels. And those were collected using an ASD instrument. There was a Gulf of Mexico cruise. We had 190 stations. This was from a National Marine Fisheries cruise in Mitch Rofer. The data collected was a CTD and a fluorometer. It's just a reminder, it's not HPLC. And the background image is a monthly composite. The cruise was from April the 2nd to May the 28th. So it was over a month and a half, close to 2 months for the cruise. And there was 190 stations collected for that survey. If you look at the x-axis is station number, and the y-axis chlorophyll. So you can look at, we have 71 retrievals, valid retrievals for the NRL N2Gen VIIRS processing, 22 retrievals from the IDPS VIIRS. So as you can see, the purple ones are from the IDPS, and the red is the in situ, and the blue is the VIIRS. And the NRL N2Gen processing is has 55% more retrievals than the IDPS. And if you look at the log-log scale, the average relative error was about 13%. And if the plot on the bottom right showing that compared to the NOMAD database, the bias or the error there is falling within the errors that they're getting from the NOMAD data set. This was a Slocum glider exercise we did off the coast of Panama City for the 8th, 9th, and 10th of November. And the blue track is from the 8th, the green from the 9th, and the cyan from the 10th. And we're looking at backscattering at 532. So what we did is we took the VIIRS image at 551, and we have algorithms to shift. If we know BB at one wavelength, we can calculate BB at another wavelength. So we move the VIIRS 551 backscattering to 532. So you can see the images. The top images are the IDPS images. The bottom images are the VIIRS images. So if you look at the 8th and 9th and the 10th, they agree. You know, the red is the N2Gen, the blue is the glider, the black's the IDPS. So they agree. They agree pretty good. I mean, the average relative error for the N2Gen was 5.75%, and for the IDPS 13.424%. Okay. So in summary, we evaluated VIIRS ocean color EDR products using processing from two systems, the Navy's N2Gen processing and the IDPS processing. VIIRS coastal ocean color EDRs compare very well with in situ ship and AeroNet sites and with MODIS. and IDPS EDR's products are over masking. We have limited number of matchups for those, and an update of the IDPS EDRs is coming in January, which will be very beneficial in evaluating those products. We're still monitoring the sensor and radiometric calibration stability using the Global AirNet Validation Network and CalVal cruises, and this would require the new IDPS updates. Follow-on cruises and validation planned in the near future. Ongoing monitoring and evaluation of the VIIRS products will continue. And the Navy's initial assessment of the VIIRS Ocean Color products indicates that they're of high quality, and we're planning on using those operationally. And it's currently currently going through op eval at our operations site in Novoceano. And I'd like to acknowledge the NOAA, the JPAS Program Office, NOAA's Ocean Acidification Program, and also the AirNet folks. Thank you.
We have time for one quick question. Anyone have any questions? Okay, so we're going to stick with VIIRS for the next talk, but instead of ocean products, we move to the VIIRS fire product, and with Chris Justice from the University of Maryland.
Good, thank you very much. This is the active fire part of the talk, and it was a presentation that Ivan, she's our very good colleague of mine, was supposed to give. And Ivan is a very smart guy. He not only is he leading the active fire stuff, but he said, "Is anybody going to AGU?" And I said, "Yes." He said, "Could you give my presentation?" And I said, "Yes." And then the day after, I got an email saying, "Well, it's at Friday at 5:30. But joking apart, he's really led this, and he's been able to really harness the Modis fire team, and I think that's really taken us to a pretty good place. And just to say that there's a considerable heritage of firework both on the GO side as well as on the AVHR through to Modis, and now we're into the VIIRS era. And to me, the VIIRS was the most important thing we could do, which was to get the continuity, because we're interested in long-term monitoring. We're interested in providing operational services to operational users that need continuity. So this is really the most important thing that I think we can do. This is just to show you this is not a small endeavor, and really to thank all of the people that were involved in building the instrument and testing the instrument, because we actually have a very fine instrument for science and application. Spectral bands for the fire, it's pretty obvious that we're still using the Modis heritage. At this point, the middle infrared, the M13, M15 long wave, but there are other bands also. The imagery bands here at the bottom, the I bands, are quite interesting for us, and we're exploring the use of those. The issue with fire detection is the dynamic range and saturation. And we've been pretty lucky on the NPP VIIRS to have a saturation better than spec, and we're hoping that we get the same extension into the JPSS. Heritage capabilities, if you look at the mid over here, if I can find the right button here, this, if you're looking at the sort of the mid-infrared range there, 4 micron, 10 micron, we've got pretty much same location, but just to say that it's really a different instrument. It's not exactly the same. So if we're going to try to develop the continuity, we're really going to have to spend a lot more time than just showing the fire locations. This is another difference between the Modis and the VIIRS, is this aggregation across scan. Aggregation is great in terms of getting uniform pixel size across scan for the imagery, but we have to be careful when we're aggregating on board saturated, non-saturated pixels and coming up with averages. So for characterization, we've got some issues, but overall it provides a good imagery for use with uniform pixel size across scan. Just as we heard previously about the DRs, we have our EDRs, active fire, these are the land EDRs over here, and the bands that we use, and they're comparative bands for MODIS. So I think most of you have probably seen this slide before. This one I like to show my students and say that in fact it didn't go up and then come down like a bottle rocket, that it was just bigger than a bottle rocket. But I like to show that. First image is exciting. We are sitting at the terminal with Ivan and Eric Vermote looking at the first image. It was coming in, and it was really a special evening. And we realized then that we'd actually got something that has tremendous amount of potential for us. And the land community overall is extremely happy with the instrument that we've got. M13 band and the I band, you can see here, and go in a little bit more detail. This is the traditional active fire red dot that we all know and love. But recognize that we've got a little bit more capability with a finer spatial resolution of the I bands too. Active fire is an ARP, and it's in the process, hopefully, of becoming an EDR. ARP was a sort of a second-class, second-tier citizen of an applications-related product. The Suomi NPP VIIRS is built on the fire detection is actually built on the MODIS Collection 4. The bands are pretty much the same as I showed, and the active fire is provided as a series of points or vector layers, which was a sort of a battle that we've been having since day one about trying to get the classification mask that we have on MODIS. But basically we have the fire locations, and we're now able to do the comparisons and starting to look at comparisons as a function of off-native view, which is important for detection accuracy assessment. This is the VIIRS for an image from Australia from April, and then for the MODIS, you can see that the time change there between 3:55 and 4:05, so direct comparison is not possible, but you're able to get a feel as to whether you're really picking up the active fires. These were from the Idaho fires in 2012, which actually really started, the Idaho fires from 2000 really started the MODIS active fire delivery systems in terms of applications users, and it's funny to see that 12 years later we're still dealing with the same problems. Good news about fires is somewhere is burning on the planet at any time of the year, so there's always a story. And the good thing about fires is that we don't seem to be able to manage them very well, so that problem's really not going away. So we'll be in business for a little while longer. The MODIS and VIIRS, you can see we've got slight differences, but overall the pattern's very much the same. We're able to take advantage of the big investment NASA made in MODIS Fire, the browse, all of the infrastructure that was for MODIS can be applied to VIIRS, and I think in terms of interagency stuff, we should really be looking at trying to save costs by using existing development rather than trying to reinvent it for VIIRS. And here's a great example, looking at the global browse, which was a system developed for MODIS, doing the same for VIIRS very quickly. You can see that here for the MODIS, you've got a gap. This is the VIIRS fires put on top of the surface reflectance. But when you go to looking at the global browse for VIIRS, there is no gap. So we've got that advantage over the MODIS system also. So here's the similarity. We have a similar overpass time, saturation levels for the bands, allow unsaturated radiance measurements for most fires. Processing algorithms are comparable, and we can be resolved with code changes. Code changes for us in terms of getting code into the IDPS and making quick changes and testing, that's not really how it's working at the moment. But improvements are being made, as you'll see, and as Jim says, we're waiting to see how this evolves, how the data system evolves. So current VIIRS algorithm, C4, we're on C6 for MODIS. Some differences, but as I said, these can be resolved. The primary drivers for the differences is the difference in pixel size, variations along scan, the aggregation scheme on board, the variations within pixels, and the way that the pixels respond to fires, and then the line spread function, for example, and then differences in the swath width and the no gaps in the low latitudes. Day-night bands getting quite a lot of buzz. I have to say, the first time I saw the day-night band for the night lights, I was just overwhelmed and said it's really very much like when we went from AVHR to 250 meter for MODIS. It's that same jump in terms of quality of data, and the day-night band is really a huge advance. It operates with better quality than we've had before. The problem that we have for fire is that we need to distinguish fires from other things that are bright at night, and that's a challenge. And really, in a sense, we don't need it because we've got the middle infrared bands from the nighttime acquisition from VIIRS. And so we're susceptible to false alarms in the day-night band precisely where we're least likely to produce problems in terms of the mid-infrared approach. But we're looking into it. This is an example. You can see the fire in the middle, but you can also see the city lights. And so you've got to sort of untangle that. But again, it's something that we can look into. So we had some anomalies, just like for MODIS, as we went through initial evaluation. Bruce Gunther will tell you that we had, in the early days of MODIS, we had quite a few trials and tribulations. This has gone very smoothly for us. We had minor bugs in terms of M13 aggregation. We had some spurious fire pixels in terms of terminator, and we had some corrupted values along the scan lines. We know what's going on there. We've got the change. We're waiting to get that change into the code. So we had this aggregation anomaly. This was a fairly simple thing, but part of the analysis just to show everybody that we've been real busy checking out what's going on. As we got to May, June, we had the problem taped and fixed it. Here's the spurious terminator. There's some early images. Again, this one's fixed, and this one is fixed too with the MX 6.3. So incremental improvements just as expected. Now, if we're going to build a long-term record here, we've got to go back and reprocess. So we've gone to beta, which I think is a good step, and it's certainly the way we did things with MODIS to get the data out as quickly as possible for everybody. And just to say that the active fire is out, but I would encourage you, if you're going to use it, to read the files associated with it. And remember that beta means that it's minimally validated, there are known problems with it, but it does allow you to get familiar with it and to start using it. Validation is going to be a challenge. We were lucky with MODIS because we had the ASTAR instrument co-located and coincident, finer resolution. We don't have that here, so we rely on other sources. This is one of the control burns that we were trying to monitor, but then you've got 1 point, and how does that help you with a global product? So we're then looking for other sources of ground data, this one from the Forest Service in terms of fires, and then using the network of airborne instruments, which are expensive, but provide us with the data which we can use. And then the spaceborne from other sensors that are up there. So we're looking for targets and opportunities for validation. Fire characterization going to fire radiatory power, something that we're looking into. And the heritage algorithm will need tuning because of the differences in the instrument. But we are optimistic, and fire radiatory power will now be included as part of the active fire product, which is something we were pushing for quite some time. It was part of MODIS, and it's been there. We've got a proving ground and risk reduction, as you heard earlier. The active fire, we're doing the sort of web-based release. We're looking at testing improving systems on the land peat, and then trying to get those put into the IDPS. Partnering with the Forest Service, just like we did with MODIS, and then the international outreach, which I think is absolutely critical for a global product to build that global community. Some examples of our website where we're showing off what we've got and where you can start to look at it and figure out what's going on. Same sort of web GIS approaches that we were adopting for MODIS, and then working with the RSAC, Brad Quayle and his team at the Remote Sensing Application Center of U.S. Forest Service, Salt Lake City. They have used the MODIS system. They're ready for the VIIRS. They want to test it out, evaluate it. These are the sorts of people that we really need in looking at these early products. Active Fires is part of their scene. They have a direct broadcast system. Again, they're able to test the system out in direct broadcast mode. Examples of their direct readout imagery. They're using this for the forest and for the NIFC, the sort of the fire center group. And then comparing that in their decision support systems that they have for the Forest Service. So looking at Aqua MODIS, NPP VIIRS, and moving forward in terms of integrating this into their operational system, which is what the NOAA program is really trying to do. So comparison between what's going on, we have two communities, but it's one group of people. We're very happy about that. I think we've got the model right. NASA scientists, NOAA scientists working together to get the best products that we can to meet the needs of both the operational users and the science community. So I think with Ivan Shizar and myself and Louis Giglio right dead center and Wilfred Schroeder, Evan Ellicott, I think we're very lucky to have this kind of program working. What's going on the NOAA side, what's going on the NASA side. These two things are synced through this linked team. I think it's the model. I think it's the way we should go. And then working with partners to get feedback and get uptake. Challenge is the latency. Getting FAR data sort of a day later, it doesn't really help people. Algorithm improvements, getting those into the system. Validation is going to be a big one, and I think data continuity, trying to develop what is the continuity product from MODIS to VIIRS. These are challenges ahead of us, but I know that we're going to be able to step up with the right level of support and with the agencies working together. So summary and conclusions. Early assessment is extremely encouraging for fire, and actually from the land community for most of the continuity products. I don't think we have any real problem areas. The land community is very happy with the VIIRS instrument. Active fires has been declared beta. I think we need to go very carefully before we say it's ready for provisional release, or what I would say validated level 1. We have to be a little bit careful. We've got work to do. And validation is ahead of us. So thank you all for staying, and those people that I paid to stay, you can pick up your money at the door. So thanks very much.
Questions for Chris while we do a speaker swap? Okay.
All right.
Our last speaker, Andrew Moulton from the Sports Center, who has the honor of the last speaker of the session.
All yours.
Thank you.
Okay, great, thank you. All right, thanks everybody. For those who he paid to stay late, if you want to save 15 more minutes, I'll throw in one more $1. Hopefully there's some beer left out in the entryway. Speaking on behalf of my colleague Matt Smith, who couldn't make the trip, I'm going to talk about the transition of Suomi National or S-NPP data products for operational weather forecast applications. So we've seen lots of great examples of the new data coming out, and we're going to talk about how we're transitioning that to other operational forecast partners. There's two other groups involved, a group at CIRA and a group at SIMS. So they didn't have presentations in this oral session, but they collaborate with us, and wanted to make sure we give a shout out to them as well. Briefly talking about the SPORT project. SPORT is an acronym for the Short-Term Prediction Research and Transition Center. We're a team of NASA, NOAA scientists, and contractors who are focused on demonstrating some unique capabilities of NASA and NOAA satellite data, research techniques, and modeling applications for operational weather forecasts. We work collaboratively, I've been talking all week, with end users and weather forecast offices, and we've been, along with our colleagues, recognized as some of these go-to places for transitioning these data sets through what we consider our paradigm of matching forecast problems to these unique capabilities. So very, very briefly, we'll talk about kind of what SPORT does. Philosophically, we tend to go ahead and work with forecasters to find the forecast problem, work through a chain where we identify the best data sets to map to that, figure out the solution, and put it in their decision support system along with appropriate end user training. With them, assess the operational impact, and at some point decide whether or not their forecast challenge is being addressed. And if it's not, we kind of revisit the process, and if it has been met, then we kind of consider that a full appropriate transition and work on developing means of getting that data to them more regularly. We've seen a lot of examples from some of the VIIRS cases where MODIS has served as a great precursor. So I'll briefly talk about MODIS, and then we'll go into VIIRS. A lot of these applications from MODIS are also going to be available in VIIRS. A lot of things we do involve false color composites. So on the left here, does this work still? Hey, it does. Here we see some false color composites from MODIS using some near-infrared and visible data to detect snow versus clouds. Sometimes that's hard to discriminate since both appear very bright. And forecasters after snow events can better delineate where snow is on the ground, and depending upon the color, maybe infer some of the depth and how much is melted for hydrological applications. On the right, we've also provided some high-resolution fog product from MODIS basically taking the traditional 11 minus 3.9 micron brightness temperature difference to focus on differences in emissivity that picks up fog at high spatial detail, especially in the complex terrain, in our case for the Appalachians in the southeast United States. We also have seen some great examples of true color imagery from VIIRS and MODIS. On the left here happens to be a MODIS case from the Deepwater Horizon incident. With true color, you get, of course, some nice depiction of the ocean color in coastal areas, but at certain sun glint angles for oil spills, it shows up very well. So this was the several days after the actual or the kickoff event, the collapse of the rig and so forth. But this oil slick that appeared in the true color imagery, you can see that swirl out here, and this was provided, in this case, to the Forecast Office in Mobile, Alabama, who used this type of data along with other data sets to supply their decision support groups with information on where the spill was and where it was going. On the right, you also see another true color image from Terra in this case, and we just talked about some fire examples, and then the nice thing about true color is when you get these high resolution fire detections, you also get a nice appearance of the smoke plume that, because it's true color, tends to be a little ashy and so forth. The color separation is a bit different, and you can pick out where the plumes are and where you may have some air quality issues for people that have sensitive health problems. Now, as we transition from MODIS to VIIRS, we have several activities underway. With all of the different spectral characteristics of VIIRS, you can take some of your MODIS applications and transition those and also do some new things. We're developing products that focus on convective storms, false color composites. Given the coverage of VIIRS, you can do those for both the continental United States and what we call OCONUS, or Alaska and Hawaii. Visibility and sealing is a tremendous forecast impact for a lot of places, especially here in San Francisco. So we have some products underway that will help to use false color to depict fog a little bit differently. And there's also some other activities related to another program in GOES-R to try and do some probabilistic fog applications that may also be leveraged for VIIRS. Other issues they're kind of traditional, but maybe isolated in certain areas. A lot of marine impacts, identifying sea ice edge for sea spray. A lot of people are also interested in land surface temperature to better predict fog and those types of events. So now we're getting into some examples that really shows the data in what we refer to as the decision support system for the National Weather Service that has been previously AWIPS. They're transitioning to AWIPS 2. And the right is a display of VIIRS data, looks like infrared data, as a swath covering most of the United States. What we do in addition to the swath imagery is put together what we consider a hybrid. So forecasters really do get value out of the high resolution polar orbiting imagery, but it's a bit difficult to use because they also then have to focus on orbit times, and so they remember to go look at the data. By blending the polar orbiting data with geostationary and kind of dropping in this high resolution depiction, you can see, I guess maybe it's not going to loop too well, but as you watch this image, there's a couple frames where the appearance of the clouds pop out in more detail. That's where the polar orbiting data is providing a quick snapshot at better resolution. That helps to define perhaps some things like wave clouds, mesoscale boundaries, and so forth that might not be detected well in geostationary, but is very prominent in the high resolution data. Previously, we showed some examples of the various false color composites, in particular the snow product that we showed. Given the spectral characteristics of VIIRS, we have several opportunities to continue these in what we refer to as RGB products. This follows some heritage from EU METSAT, who has been doing this for several years with their Severi instrument. We plan to produce the 7 or 8 products on the left there from VIIRS, ranging from dust products to microphysics products, true color, what we've seen before. Natural color is slightly different. It's pretty close to true color, but the clouds look a little off, but it uses the higher resolution I-bands. And then we also have some other attempts to do some daytime false color products to discriminate snow and fog. You'll see there are some cases here, some letters in red where the bands aren't listed. Since VIIRS, I believe, leaves off some of the water vapor bands that MODIS had, we're going to adopt those from CrIS. So it'll be kind of a 2-sensor composite to make a false color product. We've had some experiments with that already doing the air mass product in response to Hurricane Sandy. So that's kind of a neat application. You can take the hyperspectral information from CrIS and blend it with VIIRS to continue some of the products that we'd had from MODIS. So here's one quick example of an RGB product derived from VIIRS. This is the nighttime microphysics product that EUMETSAT would produce, just applied to VIIRS data. And although the colors look a little crazy here, what it's designed to do is pick out low clouds and fog as kind of this light blue to cyan color. And that helps forecasters basically take information from 4 to 5 bands of the instrument and get one quick look, rather than having to compare individual bands and channel differences. And so we're evaluating this product along with other fog products with some of our National Weather Service partners through some of these proving ground activities to see how we can further improve these, blend them with other data sets, and make more valuable use of the investment in NPP. Similarly, we saw some examples of the day-night band. Here we've taken the day-night band moonlit reflectance and combined it with an infrared image. This is something that the Naval Research Lab here in Monterey has been doing for quite a while with other visible and day-night band imagery from the DMSP era. So what you're seeing here is Sandy just prior to landfall, and the blue shade to white shade clouds are basically cold, high-level clouds that have a lot of reflectance from the moon. And the yellow clouds, because they're a bit warmer, they're kind of picking up on a warmer IR brightness temperature, but also reflecting well in the moonlit day-night band. So you're basically helping to discriminate high versus low clouds through combination of the infrared channel and the day-night band, and most importantly, preserving all of the very interesting texture detail that you get from visible imagery, both at day and night. One more application of the day-night band here from Hurricane Sandy. We saw in the last talk prior to mine that you've got a depiction of both city lights and fires. Well, here we've taken before and after day-night band imagery around the Northeast and combined it in such a way that lights that appear to be missing or diminished following Sandy appear in a yellow color, whereas lights that were present and continued after the storm appear in a white color. The blue shade here is differences in cloud cover between before and after, but we're going to continue to experiment with this type of application, and there was a news release or a press release earlier in the week talking about a black marble idea, or basically a map of the world and all of its city lights. Once that becomes more widely available and calibrated and so forth, we'll be able, we believe, to do these more reliably and do some better resolution detail of where maybe these lights are diminished. Kind of to wrap up here with a few quick instruments we haven't yet talked about. In terms of microwave data, we saw an example of hurricanes where microwave data is key because it helps discriminate the core and rain bands and separate those out from the central dense overcast. We've collaborated with the Naval Research Lab to do passive microwave data to Weather Service forecast offices, and on the right here, this is a case where we have Hurricane Isaac just prior to landfall, and we expect that with ATMS we'll be able to continue some of this work, depending upon how the polarizations work out, what's available, what's not. We may not be able to create all of the products, but we think a lot of those will still be available. We have a lot of interest in the ozone mapper profile suite. We've noticed that ozone can be a way to look at stratospheric intrusions with large mid-latitude cyclones, and once you're able to retrieve the aerosols reliably, we think it'll have some impact on delineating the Saharan air layer, which can be important to predicting tropical cyclone paths and strengthening. And then finally, I mentioned CrIS earlier. We plan to use the hyperspectral information to substitute in for the water vapor bands, and we're also very interested in that the hyperspectral data may provide some depictions of high, mid-level moisture with a little more spatial and vertical detail than we had previously. So we're thinking that the air mass product we've envisioned may be further improved by experimenting a bit with some of the CrIS channels. So in summary, support's been around for several years, and we have some proven expertise in developing and transitioning research products to the operational weather community. We're working with National Weather Service forecasters, as well as our collaborators at CIRA and SIMS, to determine some of these products to transition and how best to do that in the community. We think VIIRS has already been proven as an extremely powerful tool, especially with the higher resolution imager and day-night band capabilities, and we expect it to continue putting these data to good use in significant cases over the next several years. Thank you.
Any questions? For you diehard people, you? All right. Well, let's thank all the speakers and thank the engineers.
2120?